Okay, well, good afternoon, everybody. I hope you've all been enjoying the conference so far. Excellent. Okay, so I'm going to talk to you about a few things this afternoon. First off, I'm going to talk to you about the support for parallelism that we've introduced with the C++17 standard. Then I'm going to do a very brief section on the Coroutines TS, and likewise on the Concurrency TS. Then a bit about how coroutines and parallel algorithms can be related. And finally, I'm going to finish off with a brief summary of the Grand Unified Executors proposal. So that's the order of play. Lots of the things from TSs are all in the standard experimental namespace. That is very long-winded for slides. So we're going to assume that we've got this namespace alias in effect for all the slides, stdexp instead. So, parallelism in C++17. C++17 provides us with a whole new set of overloads for just about every single one of the standard library algorithms. We have a new first parameter. This is a magic execution policy. So, for each, you have execution policy, and then obviously your begin and end iterators and the function that you're trying to pass on. This execution policy tells the library what you're wanting out of your parallel execution. It can be a sequential execution that you're asking for, in which case it's just going to run it on the same thread, just as usual, with a few different constraints, because now it is a parallel execution, even though it's the sequential policy. And so it has the same constraints as a parallel execution, and we'll look at those in just a second. You might have the parallel policy, execution par, which means that hopefully your compiler and library are going to split up the work that you've given it across multiple threads. And it's going to divide up the work in some random order, which might vary between runs. But each individual invocation of a user-supplied function will run in its entirety on a single thread in some relative order compared to the other parts. So if you've got for each, you're going to run your single function, the function you supplied for each element. And on a given thread, it might run a random set of elements. It might run 5, 4, 7, 27, 3 million, some random order. And it's an unspecified order. It might vary between runs, but on any given thread, you can say it did these elements in this sequence. This is different from parallel unsequenced, the final standard supplied execution policy, because that one allows your functions to overlap. Now this is sometimes hard to get your head round, but if you think of it like vectorization, if you've got a vectorization instruction, if you're running for each, and what you're doing is adding 5 to every element. If your processor has vectorization instructions, it can probably, if your elements are integers, then it can probably manage to add 5 to quite a few integers in one instruction. And so you're hoping, therefore, that the compiler and library are going to work together to do that for you. So not only are your functions running on multiple threads, but it's overlapping the execution and running them together simultaneously on a single thread, if possible. But it's not just those vectorization instructions. It's generally unsequenced. So if if you're pushing things onto the GPU, then the things that the GPU can do as a vectorization is much more, there's much more scope there than what there is just on a plain CPU. And it also allows the compiler to look at your function. If you pass it something that's inline, like a lambda, to the parallel algorithm, then it has a lot more scope then for looking at that. The library can unroll a loop, and the compiler can then reorder things as an optimization. And it gives it much scope for running faster, but you can't rely on each individual function having completed. So yes, you say no, thread 1 is running elements 5, 1, 17, 3 million, and 23, but it's all mashed them up together. So you can't say which order it did them in, because it did them all together. It started all of them, then it did a bit more, and then it finished them all off. And this has further consequences. And then, of course, your runtime library might supply you with some additional implementation-defined policies. Anyone who went to the talk by the CodePlay guys this morning will have seen they had an implementation-defined policy for how to ship stuff onto the GPU. I said most of the algorithms are there. It really is. There's over 100. I've put in bold if anyone can read them. There's a few key ones there. Copy, count, for each, reduce, transform, transform, reduce, sort. Most of them are there. So a few things aren't. Accumulate isn't there, because the specification of accumulate is inherently in order. You have to do each element having done the thing, some on the previous ones. However, the parallel equivalent is reduce. Reduce is an out-of-order generalized sum. And so if you can cope with things being out of order, which if you're dealing with floating point numbers, then you might get a different answer, because the precision will change things. Now, if you have a load of small numbers and then one big one, then it can depend which order you add things up. If you use reduce, you need to cope with that. Accumulate, it has a specified order. But no, that's for you to decide if you're trying to parallelize things. No, the option is there. So yeah, for the most part, it's easy to parallelize your code if it works with a standard library algorithm. You just add an execution policy. Of course, you need to ensure that there is thread safety, because the library doesn't know what your function does. So it's going to make some assumptions. So obviously, if you're running things as a sequential policy, then it's sequential. There's no additional thread safety requirements, because it is all run on the same thread that you actually called the algorithm from. If you specify the parallel execution policy, execution par, then it's up to you to ensure that if the library runs your user-supplied code, so with a for each example, then the function that you've supplied, if you're doing sort, then a comparison, or a swap. These things, provided that the elements being worked on in different threads are different elements, then those invocations should be okay. It's up to you to ensure they're okay. So this is just like, if you've got an integer. Two threads each working on separate integers, fine. Two threads working on the same integer, that's potentially a problem. It can be a data race, an undefined behavior. And so this is just a general rule that, so for the most part, you don't need to do anything to deal with this constraint. It's only if your code does anything fancy in terms of synchronization itself that you need to worry. If you're using the parallel unsequenced policy, not only do your operations need to be thread safe, but they must not use any synchronization mechanisms. So no mutexes, no atomics, nothing that imposes a synchronization overhead. Because not only might they be interleaved, which obviously if you've got two things and they're both trying to acquire the same mutex and they're both on the same thread, and it's trying to interleave them, then you can deadlock with your own thread. But also, the whole concept of which thread they're running on might be somewhat disjoint, and they might actually look as if they're migrating across threads. Now, particularly if things have been moved to the GPU, which doesn't have the same concept of thread as the host CPU does, then the mapping might be somewhat arbitrary, and you can't therefore rely on them being on the same thread. So synchronization is just completely out. But again, for lots of things, it doesn't matter. If you're trying to add 5 to a bunch of integers, then you don't care which thread it's running on. And the other thing that that really changes with these parallel execution policies is the behavior with exceptions. If you're doing a normal for each and your function for the millionth entry throws an exception, that's fine. It will just not process any more entries and propagate the exception out, and then you can catch it in your code. If you're running this parallel and one of the instances throws an exception, it has no means of doing that, because say you're running on a compute cluster, you've got 1,000 cores, and the operations running on each of those 1,000 cores throws an exception. You can't propagate 1,000 exceptions out. So the original proposal before C++17 had a sort of aggregate exception list of all the exceptions that got thrown that all get gathered together. And the committee decided, no, we don't like that. If you're going to make this parallel, don't throw exceptions. So if you throw an exception from a parallel algorithm, even if you choose the sequential policy, it will terminate. Obviously, if the implementation provides an additional policy, it's up to them, because it's only the standard policies that force this. So for lots of code, you can just add execution par as the first parameter. And it will parallelize your code. But the thing is, this is an optimization. And like all optimizations, you need to profile to make sure that it's worth it. There is overhead to parallelizing stuff. It's got to synchronize between the different threads. It's got to divide up the work in the first place. Again, for those people that were at the CodePlay demonstration this morning, they actually demonstrated in real time what that is. They parallelized stuff on the GPU with the smallest size they had in their demonstration. It was slower. But by the time they got to the biggest size in their demonstration, it was 5 times faster. And this was just on the built-in GPU, on chip on the CPU that is in most of the computers that you buy these days have an on-chip GPU. So there is potential for optimization there, but you've got to make sure that your problem size is big enough. Now, if you try and sort 10 elements, there's no point trying to make it parallel. But actually, there might not be any point, even if you've got 100,000 elements. It's worth checking. So coroutines. Fundamentally, a coroutine is an extension of a function. The function might be suspended mid-execution and then resumed at a later time. And it will resume directly where it left off in the middle, with all the local variables having exactly the same values that they were when it got suspended. And this includes any function parameters that were passed by value. Obviously, they're referenced, then the reference is still got the same, refers to the same thing, but the referred to thing might have changed. But it does mean that then, when you resume, then it really does just resume as if it was sequential code. From the point of view of in the coroutine, everything just carries on. Conceptually, there are 2 types of coroutines. Stack-full coroutines that store the entire execution stack, and stackless coroutines. The TS is about stackless coroutines, so it is only the local function that is the coroutine itself that gets saved. This does have a strong advantage. It means everything is localized. It means that there is minimal memory allocation. And so you can have millions of in-flight coroutines. If you try to have millions of in-flight coroutines with stackful coroutines, that means you've got millions of full execution stacks. And unless your execution stack is tiny, that's going to require a heck of a lot of RAM. And it does mean that the compiler can look at the function and everything that it needs to worry about this coroutine is just there. It doesn't need to care what the rest of the stack does, how it was called, where it comes from. And so it can then make optimizations. It can eliminate that memory allocation if you're not doing anything that requires it to keep it around. Gore has done presentations. He calls this the magic disappearing coroutines, where all the overhead disappears. So there is lots of potential for the compiler to optimize your coroutines because we're using stackless ones. There are disadvantages. It does mean you can only suspend the current coroutine. You can't suspend the entire stack, which, when you use co-await to suspend your coroutine, it means that only the current function suspends and the call is immediately returned to the caller, which can have knock-on consequences about the way that you structure your code. So you need to be aware of that. It's, in some ways, some cases, it's not what you would ideally have chosen, but there are ways around it, and you can have to design your code with that in mind. So in C++, what does a coroutine look like? It's just a normal function. The crucial is it must use in its implementation, in the body of the function, directly there, not in some nested function call, but directly there in the body of the function, use one of the 3 magic keywords. They start with co keywords make coroutines. It can be wait, co-await, which will conceptually wait for something, co-yield, which conceptually returns an intermediate value to the caller, but then allows your coroutine to be resumed, and co-return, which is an I'm done, if you resume me, then bad things will happen. Final result coming out of your coroutine. And then the return type of the coroutine must be something that is designed as a coroutine return type. And you must have a corresponding coroutine promise for that, which is an internal data structure you specify by specializing the compiler's coroutine traits. So, co-return looks like a return statement. Co-return some value, and that returns the final value. Co-await, you pass in some awaitable thing, and you're telling the compiler and library that you're going to wait on that thing to be ready. And if the waitable is not ready, then you're going to suspend the current coroutine and return to the caller, who will then hopefully do something and then your coroutine will resume at a later point, back right there after the await call. Co-yield is similar, but the intent is that you yield with a value, and so that value then gets somehow propagated out to your caller with the proviso your coroutine is now expecting to resume on the next line. So this is different from a return. It's expecting to resume, and it will then carry on straight away from the following line. Now I mentioned coroutine promise types. A promise type is how you specify how the coroutine internals get that correspond to the return value. And it specifies what the compiler and library will do when you put in at those co-return, co-await, and co-yield locations inside your coroutine. How it deals with suspension, what happens, how the return value gets handled. And then they also have this concept of an awaitable. The awaitable is something that you can wait for with co-await. And often they will be related types. So you might have something that is both an awaitable, you can wait for it with co-await, and has a corresponding coroutine promise type so that you can use that type as a return value from your coroutines. But they're not necessarily the same. So as an example of something that is going to be the same, or you might expect to be the same, is something like a future from either from the C++ standard directly or the coroutines, the concurrency TS type futures. Then obviously a future is a value that is a placeholder for a value that's going to be available at some point. And so you might have some function that's going to give you that, a future and some value. And so then inside your coroutine, you can co-await on a function that's going to generate you a value. And it will suspend your coroutine until that value is ready. But then you could also return from a coroutine a future. And so then when you do, then it will wake up anything that's waiting on it. Now, if these are just standard futures or standard experimental futures, then you can then use them with all the rest of your code. And if it was a coroutine that returned that future, and the coroutine got suspended because the future wasn't ready, then when you wait for the future, then it will check, depending on how the library's been implemented, and make sure that the coroutine gets resumed. And when the coroutine is finally finished and the data has been returned with that co-return call, then the future will become ready, and the code that's waiting for it will finally return. So this provides a means of meshing coroutines with code that uses futures, like from standard async or from a standard promise. Whether or not your library provides that, the standard library provides that integration varies. I think the Visual Studio 2017 implementation does provide that for standard future, but the Clang 5 version doesn't yet, if I remember rightly. But they might then add it. You could also write your own future-like type, mylib future instead of standard future, and then you could implement that yourself. It's not particularly complicated. Now, stackless coroutines work nicely if everything down your stack is a coroutine, because actually then you can say co-await on something that I'm waiting for, and it returns up to the caller. And the caller, well, immediately it doesn't care about what result you're returning, so you've got some form of future value coming through, and then you do some more code, and then at that point it will say, oh, well, actually, now I do need the value, so I'm going to co-await on that future that I got back and suspend that coroutine, which obviously, it's nice to propagate all the way up. And actually, you could then, so if you're doing that, and you want to work with parallel algorithms, then you could actually, the implementation could provide a custom execution policy for your parallel algorithms that makes your parallel algorithm work as a coroutine. So you could have standard for each, parallel as coroutine from begin to end, do stuff. And then you can then co-await on that returned future that you get from this invocation of parallel for each. So that's the first way that we could potentially integrate coroutines and parallelism, is because by having this custom execution policy that allows us directly to mesh the two. Okay, so we'll just leave coroutines aside for a second, and we'll have a look at the concurrency TS, which is extensions to futures, is probably the core bit, and so that's what I'm primarily going to focus on here. There's also other things. There's also latches and barriers, which are synchronization objects for events across multiple threads, waiting for five events to happen across a load of threads. You have a latch, and then when all the events have happened, the latch becomes ready. Barriers are similar, but they're reusable. They are for when you've got a bunch of threads that are working together, and they all need to be in lockstep in some fashion. So they all do their first chunk of code work, and then they hit the end, and they all wait for the barrier, and then they loop round again. They do the next chunk of work, each thread doing its own relevant parts, and then they all wait at the barrier again, and so forth. Now, the latches and barriers are actually now being targeted, hopefully, for C++20. They've been pulled out of the Coroutines TS, and the committee has said, yeah, we like these pretty much as is. There might be a few minor tweaks, so they're going ahead with C++20. We've also got atomic smart pointers, so atomic shared pointer and atomic weak pointer. These allow means of, standard C++ shared pointer that we all know and love. It works across multiple threads in the sense that you can have, each thread can have its own shared pointer instance, and they can all be referencing the same object, and the reference count all works nicely. Now, what we get from atomic shared pointer is that we can have a single atomic shared pointer instance, which is referenced from multiple threads, possibly because it's like the a pointer to a master data structure. And so everyone has to come and say, can I have that, have the pointer, please? But then somebody might want to come and update it. And so rather than having the mutex lock round for protecting that master pointer, then you can just make it an atomic shared pointer. And then each thread can do that, and it is inherently safe. And that's also been targeted for C++20 now. And that was, the spelling has changed. In the TS, it was atomic underscore shared underscore pointer of T. And now it is atomic angle brackets shared pointer of T. But, no. What's an underscore to an angle brackets between friends? Anyway, so I'm not going to talk any more about latches and barriers and atomic smart pointers. If you want to talk more about them, then come and catch me later. But for now, I'm just going to focus on the futures part, because that is what is relevant to parallelism and coroutines. So a continuation is a new task that you want to run when the future is ready. So you've got a future which is some task that's going to generate some value for you. And you say, well, when that's ready, then I want to do another calculation with that value. And so you can either wait for the future and then spawn the task, possibly as a new asynchronous task, using standard async or a thread pool or something. But alternatively, with the concurrency TS, we now have this new member function on the future, then. So you can say, when the value is ready, then do this. And the library will take care of automatically scheduling your new task when that value is ready. And you can specify all this up front as soon as you've launched off the first task. You can specify what to do next without having to wait for it to be ready. Now, obviously, futures, as in directly standard future and therefore standard experimental future, which is based on the same, are one-shot things. So you can only use it once. You can only get the value out once. So if you specify continuation, then you can't get the value out any other way. That value can now only be retrieved by the continuation. And so the source is no longer valid. And secondly, the continuation itself will get a future as the parameter, because the future might contain either a value or an exception. And so rather than having to have different continuations for the different options, there's one function that we get called if we've got a value and another one that gets called if we've got an exception, then we already have this packaged up thing of a value and an exception. It's the future. So that future itself gets passed in to the continuation when that future is ready. So a continuation always receives a future, but it always receives a future that is already ready. If you try and wait, it will not have to spend any time waiting, because it's guaranteed to be ready when the continuation is invoked. And it does consequently mean, of course, that you can only have one continuation per future, though, of course, that continuation itself will return a new future, so you can chain them on, have a whole series, but only one at a time. So let's have a look at some code. We have some function that's going to find us the answer. It's going to return us a standard experimental future. We have another function that's going to process that returned result, and that takes a future as a parameter. So we spawn our function, we call find the answer, it gives us a future back, autof, and then we chain on our continuation of process result by calling f.then. So f2 on this slide will be an experimental future for a string, because the return result of process result is a string. If the future contains an exception, then the exception gets stored in the future that's passed to the continuation, and like normal futures, if you then call get, it will throw. So the concurrency TS has this nice function, make exceptional future, which directly stores the future in, so you don't have to try and catch and store a value directly or use promise.setException or anything. You can just have a future that already contains an exception. So we call fail, and that's going to give us a future that holds an exception. We put on the continuation with a call of then and passing in our next function. And that will then throw when it is called by the runtime library. And so the call to get inside next will throw, which means that the future that is returned from our continuation, that f in foo, will hold an exception. So when on the next line in foo we call f.get, that will itself throw. So it is the same, our runtime error that we created at the top is then propagated across the chain and then comes out with the final get. Of course, next could catch and handle that exception, in which case then it wouldn't be propagated, it would be caught and handled, and then the call to get at the bottom there in foo would then not be throwing an exception because it was handled inside next. If you just want the exception to propagate and you don't want to handle them, and having a function for your continuation that takes a future as the result, as the parameter, is undesirable for your circumstance, possibly because you already have a function that you want to use that doesn't take a future as a parameter, then it's easy enough to wrap it in a lambda. I've specified out the lambda function parameter there, is an experimental future, but of course you could just type auto. Our lambda that takes auto f and then returns the function, a call from what we're actually wanting to. And that f.get will throw the exception if there was one, which will then be propagated out and caught, so you don't have to worry about what happens on the exceptional case. And if you don't like writing lambdas there, then you can just write this unwrapped function, which contains a lambda to deal with it for you. So then you can say unwrapped process result, and that will unwrap the value and propagate the exceptions if there were any, and call the value that it got from the future. Call the supply continuation. So that's there as a helper. Obviously, it's not part of the TS. You'd have to write it yourself. You can copy it off this slide. The PDF will be available from CppCon at some point, so that you can copy that out and call it what you like if you don't like the name unwrapped. Continuations also work with shared futures, but they have some changes. Shared futures allow you to call get multiple times, but you get a const reference back. And so likewise, you can schedule multiple continuations with shared futures. They can't take a normal future as the parameter, because otherwise you might remove the value that was then trying to be propagated to all the others. So they take a shared future as the value. And the source future remains valid because, hey, there's no reason not to make it. And so you can chain multiple continuations on the same future, either directly there or across all the copies. So we have some code, we've got some function to find the answer, and two continuations we want to use this time, next one and next two. So we call find the answer that gets the future, we share it to give us a shared future, and then we can chain two continuations, each of which will get the value from find the answer. And of course, they will have different types because the continuation functions return different things. So f2 will return an experimental future of void, and f3 will be an experimental future of int. And that's just how you might expect. Alongside continuations, we also have this concept of being able to wait for multiple futures, because futures are all very well, but if you've got a whole bunch of them, then sometimes you want to say, well, when one of them's ready, and I don't care which one, then I want to do some stuff. I want to process the first result that comes back. Now that might be because you're actually using, you've got a whole bunch of cores available and you're not doing anything meaningful with them. So you can say, well, actually, I don't know what the best way to calculate this result is, so I'm going to launch off 5 threads that's each going to calculate the result in some different fashion. And then when one of them comes back, the first one that comes back with the result, I'm going to use that. And so when any of them are ready, then I'll do some processing. And there's 2 ways of doing it. You can either pass when any and pass the futures one at a time as function parameters, or you can have some container that contains a load of futures and you can just pass the begin and end of the container. And then depending what you do, you either get back a future that holds a tuple of the futures, or you have comes back something that holds a vector of containing the futures that you pass through. And in either case, this is they're stored inside a structure of a when any result, which the key thing about that is that it tells you which one of these set of futures it was that was the one that woke you up. So you don't have to go through and say, are you ready? Are you ready? Are you ready? Are you ready? Oh, wait, that one. If you've got a whole set of 100, then that's a bit messy. And so it just tells you, it was the 97th. OK, fine. I can take the 97th and use that. And obviously, you get the futures back, because if they were standard experimental future that you got passed in, it's a one-shot thing. So you've just passed it into your when any. And so therefore, you don't have it anymore. So you then need to get it back in the result. So yeah, it's great for speculative tasks. If you've got something, it's like, okay, well, when the first of these is ready, then I'm going to do something. So say you're writing a web browser and you've got download 5 images in the background. When the first one comes back, then I'm going to actually update the rendering of the page. I don't care which one it is. I'm going to do that processing, and then I'll do something else and wait for the next one or whatever. So that's great. So we have 2 functions that create us some futures, foo and bar. We then move those futures into when any. This is move because it's passed by value. And experimental future is a move any type. And then we can, it just returns an experimental future, so you can chain a continuation. So f3.then. Instead of just one, you can wait for all of them. This time it's slightly simpler because the return value doesn't need to tell you which one it was that woke you up. They were all ready. That's why you woke up. But again, we've got the 2 overloads. And so we can spawn 3 futures, and then we can wait for all of them. OK, so how does that relate to coroutines? We've got coroutines from the Coroutines TS. We've got continuations from the Concurrency TS. How does that work? Well, in some sense, futures are ideally suited for coroutines. They hold a value, which is going to be available at some point. You can already wait on them in normal code. They can represent asynchronous tasks. And you can create one already that directly holds a value. So these map very nicely to coroutines. And so you might hope that your implementation of futures would work nicely with coroutines. So the compiler needs to know what to do with it. And so the library has to specialize coroutine traits to say, yeah, we can deal with coroutines. You just deal with it like this. If you're trying to wait on futures, that works fine. And then operate a co-await, which is how do we wait on a future when we're in a coroutine. But once it's done those 2 things, it all just works. And so there's a nifty feature in the continuations part, which is that if your continuation function returns a future rather than a value, then that future just gets subsumed into the final return value of the continuation. So if your continuation function returns an int, then the result of your then call is a future holding an int. If your continuation function holds a future to an int, then the return from your then call is still a future of an int rather than a future of a future of an int, because otherwise that just gets too messy. And so if you have a coroutine, then if you're trying to use it with futures, your coroutine will return a future. But that's okay, because you can use it as a continuation, and then that coroutine return of a future will then just get nicely mapped through. So in this case, our continuation returns a future holding a result. And then the final result of our continuation is again a future holding a result. And it doesn't matter that that continuation was a coroutine. The library doesn't care. It's just something that returned a future. What about coroutines and parallel algorithms? I mean, I mentioned parallel as coroutine as a possible execution policy, but what else is there? So if we're writing parallel algorithms, we're using parallel algorithms, then one thing we care about specifically is processor utilization. Now, we've got 1,000 cores, and we're trying to stick a load of work on them, and what we don't want is for those cores to be sat blocking, doing nothing if we can help it, because that's just wasting available processor resources. So if we have blocking operations, which you get normally with futures, then they hurt that. They complicate the scheduling. They occupy a thread. They can force us to do a context switch, which is expensive as far as the OS is concerned, and just generally saps our overall performance. So coroutines allow us to turn blocking operations into non-blocking ones, because we say co-await on something, and this suspends our current coroutine and returns to our caller. And the coroutine can then be resumed when that waited for thing is ready. But in the meantime, the current thread can still do something. So this works well with parallel algorithms. The issue is, of course, that if the suspension is a nested call, then a stackless coroutine, like we have with the coroutines TS, just moves the blocking up a layer. So if F calls G, which calls H, then if H is a coroutine and uses co-await to wait for something, then that just resumes execution in G. But if that then needs the result of H, then it has to block, unless it's also a coroutine and can use co-await. And then likewise, all the way up the call stack. So if we make everything a coroutine, we're fine. We have H, which is a bottom level thing, returns a future. The result we get from co-awaiting on something and processing it, and then we use co-return because we're trying to return a value through our future from a coroutine, and then likewise in G and F. And that means that then we can use that when we're building a parallel algorithm as an implementer. So if you're trying to implement something with a parallel as coroutine algorithm, then you provide an overload that then internally will look something like this. It uses something to divide up your data and co-awaits on it so that that can be a parallel task. And then when it's ready and it comes back, then we're going to do recursive calls, but it's a recursive call to this function, which is itself a coroutine and is going to somehow be parallel. And then we're going to need to co-await on those results in order to combine them somehow, which again we want to be parallel, and then we're going to wait for that to finish in order to return our final result. So then the way that all these subtasks get scheduled is then an implementation detail of the library, and you don't have to look at your code and say, how do I post all the tasks onto my thread pool that's running this, or whatever, or how do I post it up to the GPU? This is completely hidden. The runtime library, in its coroutine traits, deals with making sure that when you co-await on something inside your parallel algorithm, it gets passed to the thread pool. And so from a user's perspective, it looks like magic. But all that magic goes in the operator co-await overload and the coroutine traits specializations. OK, so the final thing. Executors. What do we mean by an executor? I mean, the core concept of something of an executor is it's something that's going to run our tasks. Controls where and how they get executed. but quite the details, people have different use cases and can lead to quite different approaches for how you implement and specify an executor. What kind of tasks have we got? Where do we want them to run? What relationships are there between tasks? Are they just completely independent, or are they in some crucial way dependent on each other? Can they synchronize with each other, or not? No. Can they truly run concurrently, or do some of them have to run sequentially with each other, but they can run concurrently with some other batch over there? No. Can they run interleaved, like with a parallel unsequenced? No. Can we move them around across threads? Can they in turn spawn new tasks on the same executor? Can they wait for each other? All these are important questions. And we want to allow as many of the, yes and no as different answers for all these questions without fundamentally compromising our framework. And then we have other questions. Can an executor be copyable? What would that mean? Are they composable? Can you somehow build a composite executable out of individual parts? If you have a task that is running on an executable, and you have some form of handle to that task, can you get the executor back in order to run another task on the same one? Or if you are running a task right now, and you know that this function that I am in has been called from an executor, can I get an executor find out which executor that was in order to run a new task? As some form of continuation of the current one. So these are, again, important questions. There have been, I think I counted something like 23 papers on this topic over the last few years from the C++ committee, of which the latest is P433R2. That's the second revision, and therefore the third paper with this number, of a unified executors proposal for C++, which provides us with many customization points in order to allow as many possible answers to the previous questions. It has a basic concept of what we mean by an executor in this case. It is something that is copy constructible and equality comparable. So you can say, is this the same executor that I had over there? And I can freely copy it around. It provides a context member function, which tells you what the execution context is. So for example, if you're trying to implement a thread pool, then your execution context is the thread pool itself. And then the executor is something that tells you to run the task on that thread pool. So you can pass around your executor because it's just a handle. And you can copy that around willy-nilly, and any thread that has a copy of that executor can then launch a task on that thread pool, which is what the context fundamentally is. But the details of what a context is specific to the executor type. And then fundamentally, you somehow have an execute function, whether that's a member function or a free function, in order to actually launch tasks. And the way that we get to all the different properties that we wanted to know, can things run concurrently? Can we bulk execute things? Whatever. We have this require member function, which provides overload. So if you need a specific property from your executor, then you say, I require this property. And either it will compile and work because it can provide you that property, or it will fail to compile because it doesn't. And the framework can then allow you to build everything else from there. So let's have a look at some code. We have some executor, my executor, and we're trying to run a function. So you can just say execute some function. That works. But we don't know quite what it's going to do in terms of how it's going to schedule and execute our function. So you might think, OK, well, we need something specific. We need some properties on that. So I say, I'm going to require that from my executor, I need it to be two-way communication, so I need to know when my task is done. But I'm only going to execute one function at a time. And then that gives us a combined executor from our source one that has those properties. And if we can't do that, it will fail to compile. And then we can call 2a execute of our function, and that will definitely then give us a future back, which we can then wait on in order to know when the task has been done. There's a whole bunch of properties that you can require. Right? You can launch your task and say, well, I don't need to know because I've got some other mechanism of knowing when it's done. Or I want a future back. Or this function that I'm passing you now is a continuation of this other function which I'm passing you a future for. No? So this works with the continuations from the concurrency TS. I only want to pass in one future at a time, one function at a time. I want to pass in a whole bunch of functions at a time and get in order to bulk execute things, because then you don't have the overhead of filling up your task queue one at a time. I want to guarantee that I will never block. The execute function is never going to block. It's always going to run the task in the background on some other thread, or add it to some queue for running later, or something. Or I want it to always block because when I call it, I want it to run the function right now. Or possibly you want it to do whichever is most appropriate for it, possibly block. Or you want to say, well, the functions that I'm passing in are in some continuations of the current task. So when the current task is done, then start these new functions, and not before. Or alternatively, they're independent things, so don't bother waiting for me. You can start them straight away on some other thread. And there are more. There's a whole bunch of properties that you can query. And the framework is extensible, so in theory, you could add extra properties for the continuations that you as a library implementer are providing. So when this finally gets widespread implementation, then you might find that each implementer provides a few extra properties that are just for them. This can then interact with the parallel algorithms, because you can provide a custom execution policy that says, spawn the tasks for this parallel execution on my executor. It's also natural to think that you can do the same with the concurrency TS continuations. So I want to call this continuation and do it on an executor. Now that's actually worked quite well, because the TS as specified runs the continuation on an unspecified thread. You don't know whether it's a new thread. You don't know whether it's a pool thread. In theory, it could be your GUI thread, when you don't want anything to run on the GUI thread unless you're intending it to. Any thread in the system. So it's with the concurrency TS, this is deliberate. It's a TS. We're asking for it's implemented like this in order to get maximum feedback, and allow library implementers maximum scope for seeing what their users want. But with an executor framework, then it makes sense to be able to say, I want this task to run on this executor. So there's different availability for all these different parts. There is not a shipping implementation that I'm aware of that supplies all of them. Visual Studio provides the Coroutines TS. Clang 5, if you use it with libc++5, also provides the Coroutines TS. The HPX team have got parallel algorithms and futures with continuations which look like the concurrency TS ones, and they have some executive support, but it's not quite the same as this proposal. My Just Thread Pro library provides the concurrency TS and integrates with coroutines, and I'm working on parallel algorithms. But the whole lot is not in any one implementation. So at the moment, you're going to have to choose piecemeal or actually help work on one of the open source implementations. My book covers stuff on the parallel algorithms and the concurrency TS. There's nothing on coroutines in there. The early access edition is available for the second edition, and I believe there's a 50% discount code that you should all have received by email for being at the conference. If you're actually interested in JustThread Pro, then go check out the website. It's a commercial library rather than open source. So we have a few minutes left. Has anyone got any questions? There's a couple of mics. How far? That one.
So does that mean that if you're using it in your main function, coroutines in your main function, that you have to make your main function return a coroutine?
I don't think the Coroutines TS supports main being a coroutine.
Okay.
A lot of slides back, you had a shared future where
Yes.
you continue at 2 continuations using .n twice.
Yes.
How will that run? Will that run one and then the other, or in parallel, or is there any?
It's
unspecified.
Okay, so if you schedule multiple continuations on a shared future, then is there any guarantee what order they run? And well, no. The TS things run on unspecified threads, and they run unspecified in unspecified times and orders. So if you schedule multiple, they might run concurrently on separate threads. They might run sequentially on one thread in some order. You don't know. That's a deliberate, again, decision to allow TS implementers maximum scope.
And that will change if the executor comes in, because then you
if it comes, then you can then say, what does the executors require? No, what does it specify for that?
And the other question was, you mentioned a wait, when any, so you can wait for any of the continuation or any of the tasks to be ready. What if you would want to wait for the next? How could that be achieved?
Okay, so you call wait any, and it tells you that one of them was ready.
Yeah.
But when you get the result back from that, then you've got the full set of futures that you waited for. So you can then pass those back in to a subsequent when any call if you want to wait for the next one.
Oh, you get them all.
Yes, you get them all back.
Thank you.
Okay.
You had some sample code there for a parallel func that called parallel divide and then parallel combine at the end. It was sprinkled with these co-await, co-return.
Yes.
And I looked at how that would look if you did it with promises and futures instead, and you just chain them together with then, and at the end you have a when all, then parallel combine.
Yes.
And it seemed like about the same amount of code, but the futures promises one seemed to be more refactorable in that you didn't have these syntactic constraints of having to put the keywords everywhere and it breaking when you pulled out a piece of it. Have you seen good examples of places where coroutines really give a big benefit over just using futures with an executor that would be completely synchronous? Something where when you schedule on an executor, it just runs the thing.
Yeah, I mean, there's plenty of examples when you're looking at real code. Obviously, this is code to go on a slide. The advantage, if you use something like that where you're using coroutines in a parallel algorithm, then it means that the whole thing is a coroutine, and you can disable the parallelism outside of that by putting what's the context that it's running on, and so it punts that decisions out of the code that's right there into the library that's dealing with the parallelism at the back, which could then put it all on a single thread and just interleave all the calls as various bits become ready. But in some circumstances, then just changing it with promises and futures is just the way to go. I know it isn't a panacea. It's not an answer to everything. Sometimes it makes the code clearer, and other times it doesn't help. So
in the coroutine case, who's deciding? Like, which part of the program decides whether it's like multi-thread or not? Is it coroutine traits?
Yeah, it's coroutine traits and operator co-await, which... And
those are global, like operator new? So you can be
well, operator co-await is overloaded. So you specialize it for your... it picks the right overload for whatever type it is. And then... but it works together with coroutine traits. It's rather nifty inside. So if your coroutine traits allow you to have an await transform. If you co-await for something, then it transforms it into something else before it looks up operator co-await. So it's really quite nifty and allows a lot of scope for changing things around. It took me a while to get my head around the scope of Coroutines TS and how actually really good it is, and the scope that we have for completely messing up your code, but in a good way.
Thank you.
We actually have several questions. First of all, you mentioned GPU. So please clarify, does that mean that if I use a parallel version of an STL algorithm, it can actually offload some work on GPU?
Yes, and the CodePlay example this morning did just that.
Well, how exactly this happens?
I think their implementation, their compiler is a wrapper for 2 compilers. And so you pass it your CPP file, it compiles it for the host CPU and for the GPU, and then at runtime, depending on where it ships some of the work over to the GPU.
Okay, so now developers of the C runtime and compilers are actually required to adapt some GPU operations for this particular thing?
Yeah, and so yes, I mean their implementation requires compiler support. So they're shipping a compiler that does it. So.
Okay, yeah, that's pretty cool actually.
Yeah, I think so.
Well, this brings to another question. I was wondering, is this this seems like a really hard work and big amount of work. How it is actually applicable? I mean, usually when you parallelize things, you separate your work into tasks, and then you make task-based parallelism. And it seems like a very corner case when you want to parallelize actually one algorithm, because usually you have many algorithms, and you have some kind of pipeline, and maybe you have a dependency graph, but parallelization on a level of a particular algorithm looks like just some corner case.
Yeah, in some. Okay, so sometimes that is what your problem is, and you have a big problem, which is process this large chunk of data all the same, and you can use one of the STL algorithms to it. Lots of problems of other varieties you can rewrite as a call to transform reduce. Transform reduce is so general that you can do a heck of a lot with it. And so parallel transform reduce, you can do a whole bunch of things. But sometimes that still doesn't work because, yeah, you have a pipeline, in which case this doesn't solve your problem. You need something else. There are pipeline proposals before the C++ committee, but they're not in any TSs or in the standards draft yet.
So basically, the committee decided that this particular approach is applicable to many situations in real life.
Yes, and it really is in practice. There have been libraries shipping that do just this for a long time. And so we finally got a standard API for it in the C++ standard, rather than having to use the vendor-specific implementations and their APIs.
Okay, great, thanks. And the last questions. You mentioned that when we throw an exception from a function that is executed in parallel, so for example, for each, we terminate, right?
Yes.
But we could have accumulated all exception, but the committee decided not to do that.
Yes.
Right? Why?
Because it's messy. What would the user do with 1,000 exceptions?
Well, we have nested exception preservers, we have all kind of stuff. I'm pretty sure we might come up with some solution. So there should be some fundamental reasons why we don't want to do that, right?
It's messy, it's complicated, it makes the implementation of the parallelograms really hard.
Well, it's C++, right?
Yeah, but it also adds overhead because there has to be synchronization. This grand list has to be synchronized across the things. It's something that the implementer said, we don't want to do this. If you're on a GPU and exceptions are not the same, so it complicated like the task of shipping stuff to GPU. If you wish to write yourself a parallel algorithm that propagates exceptions, feel free. No one's going to stop you, and you can.
Yeah, we already did it, actually.
Or alternatively, badger somebody else who is already writing one, an open source one, and get them to do one. But
thanks.
Okay.
Thank you for wonderful presentation. I have a question. I feel the concurrent TS is similar in Microsoft's PPL task, I think. So the Microsoft PPL task is Microsoft PPL task compliant with concurrent TS?
In some ways, I believe that they have some of the same sort of concepts, tasks and continuations and futures. Yeah, I don't use the Microsoft PPL, so if you want to know about that, then you're probably best nabbing one of the Microsoft guys. There's quite a few here today, so.
Okay, thank you.